Already.
Salut, ça va? Ça va, ça va.
Bonjour, très bien. Tout se passe bien?
Ça va? Bon, c'est parti.
On attend juste l'intervenant qui est à toilette.
Jean, je suis ravi, après ton résultat.
Oui.
Top, top. Start recording.
Je coupe tout et je ferme la salle.
Ouais. Moi, je reviendrai. La vidéo, elle restera en public. De toute façon, je viens tout à l'heure, on fait la.
C'est en direct sur la chaîne.
Peinture bretelle, c'est en direct, c'est enregistré.
Et les sons?
Le son, il est bon, regarde.
Ah, donc on a un direct?
Oui. Donc là, on t'entend sur YouTube. Il y a au moins 0 personne qui t'entend. Pour l'instant, pour l'instant. Voilà, personne pour l'instant. So do I feel good for this? Yes.
Is there a mic? Do you
No, that's just a platform.
Okay, right. If you want to pack on Saturday evening, probably. Okay, don't get to go much. Ah, good.
Okay, so hello everyone, and welcome back to our series of internal Colloquium of IPHT, the Seminar General. Today it's a real pleasure to have Tim Cohen. So Tim did his PhD from Michigan and then had positions at SLAC and Princeton before taking his position in Oregon. Now he's also at CERN. He's a well-renowned expert on particle physics, and in particular today he's going to tell us about the geometry of particle physics.
Thank you very much. So yeah, it's a pleasure to be here. I had the honor of serving on a PhD committee on Friday, so I'm kind of getting both ends of this Clay experience, and it's really been fun. It was one of my bucket list things while I'm here at CERN that I get to spend some time with you here outside of Paris. So thank you very much for having me. today I'm going to tell you a story about some perhaps, well, some of you may be familiar with these ideas, but if you're not, I'll hopefully show you some interesting connections between the ideas coming from geometry in the sense of Riemannian geometry and the way they appear in particle physics. So I'll review a bit of the theoretical background, and then I'll talk about some connections with phenomenology, in particular with thinking about particle physics and the LHC. And please interrupt me with questions. Happy to be slowed down if things are unclear. Okay, and this picture here will hopefully become clear by the end of the talk. Okay. All right, so what do we mean by geometry? We mean what you think it means, okay? So we're going to be talking about curvature. In this case, it's going to be the curvature in the field space for these field theories. And we're going to have a notion of a metric. Okay? So geometry in the title means what you think, and of course particle physics also means what you think, right? We're talking here about the Standard Model, and in particular, kind of understanding possible extensions of the Standard Model. So really, I'm coming at this with a perspective for beyond the Standard Model physics for searching for new physics at the LHC. Okay, so that's what the title is about. And again, I don't have to tell you, but just since I know there's a variety of interests in the department here, you know, when we talk about the LHC, I think the best way to think about it is that it's just the world's largest microscope, right? So in natural units, right, we're probing when we set h bar and c to 1. That's talking about interactions with a few number of particles, at least in the hard scattering. And we're talking about very high energy collisions. And when you put all of that together, right, the understanding is that high energy probes short distance, right? The short de Broglie wavelength is probing the most microscopic scales in nature. And so you should think about the LHC in this context, right? That we're really just that it's a huge microscope. Okay. All right. So what I'm really going to tell you here is not about the geometry of particle physics, but more specifically about the geometry of effective field theories. So in the colloquium, I'll talk a bit about what I mean by effective field theory, especially in the context of extending the Standard Model of particle physics. And then eventually I'll come back and make this connection with geometry and explain why thinking about effective field theory through this lens of geometry has given us insights into possible ways that new physics can appear at the LHC. Okay. All right. So what's effective field theory all about? Well, you know, it's really a remarkable tool whose purpose is to systematically coarse grain a system. Okay. So basically, you know, physics is all essentially effective field theory in the sense that effective field theory really makes precise this notion of combining dimensional analysis with some kind of fancy Taylor expansion. Okay, we usually call it a power expansion in effective field theory, but it's that combination together which give us a way to a systematic tool, okay, to understand what happens when we kind of zoom out from a system. So very much in the sense, right, that the LHC is probing short distance scales. The hypothesis is that there's some new physics to be discovered that may be a little bit deeper, a little bit higher in energy than what we can probe directly. And effective field theory gives us a tool that allows us to parameterize that unknown new physics in a way which is largely agnostic to the details of the microscopic description, right? So the kind of spherical bunny in this case, right? So this would be the leading approximation, and then in principle, right, you can sort of imagine systematically adding more and more features as an effective field theory expansion and ultimately reconstruct what we care about, which is the true microscopics. Yeah, and actually I had no idea, but I've seen a lot of bunnies hanging out in Paris. We were at the Rodin Sculpture Garden, and there were bunnies everywhere. So, it's very appropriate for the context here.
Not the spherical ones.
No, not this rodent ones. They were indeed. Okay. And we're all familiar with this. And again, I realize this is maybe too zoomed out for a lot of you, but the idea, right, is that EFT is essentially to make this idea that EFT is capturing a systematic expansion more precise. You can really think about it in terms of this classical example, which is the multipole expansion in electrodynamics, right? We have some. This is our EFT description, which is just that there's some dipole, but actually if we zoom in microscopically, right, we see that there are two charges separated by some distance. And in fact, the dipole formula is simply the leading approximation of a multipole expansion, which is phrased as a ratio of dimensionful scales, right? So there's this microscopic scale, which is the separation between the two charges. And then there's this macroscopic scale, which is the distance where we're making our measurement. And so you can, so this is a direct analogy. Of course, this is purely classical, but with what we do when we work with quantum effective field theory is exactly the same kind of expansions hold. Okay, so again, the idea is, we're measuring, if you like, what the LHC is doing is we're measuring the field out here very, very precisely so that we can hope to capture effects beyond the kind of leading universal term, okay? And again, this really comes down to the principles that drive us in particle physics, which is reductionism. This idea that we keep zooming in and we keep learning more about fundamental features of nature, okay? So I think I've kind of belabored the point enough, but again, it's just this notion, right, that short distance tells us about high energy, and we're really, this is what we're after, right, is to understand what lies beyond what we already know in the standard model particle physics. Okay, and this notion of EFT is extremely general. Here I'm just selfishly advertising my own work, but just to say, for me, using this tool and finding different places. So, just to give examples, we used it for doing some precise calculations relevant for dark matter phenomenology. It shows up in detail when we want to talk about how to map from microscopic models onto EFTs at the LHC. I've even been using it in this context of so-called Hamiltonian truncation, which is some way of doing numerical quantum field theory for strongly coupled systems, and also doing EFT in de Sitter space. So just to say that, I'm not going to get into the details so much of how to define an EFT and so on, because this is a colloquium, but the basic tools and the ideas here, especially for the students, so you understand that once you learn, especially the modern way that we think about effective field theory, then as long as you are finding yourself in a situation with a separation of physical scales, it's likely or inevitable even that there's some EFT description which may be waiting to be discovered. Okay, so that's kind of and if you're curious, I also advertise these lectures that I wrote now. They're starting to get, this is starting to make me feel old, but 8 or so years ago, where especially in the beginning, I really tried to lay out this kind of modern way of thinking about these. Okay, so we're here now. Okay, so I gave you kind of this context for what I'm going to talk about. So I want to get a little bit more into discussing effective field theory and its applications at the LHC. Then I'll connect effective field theory and the ideas of geometry. We'll take those connections and apply them in the beyond the standard model context, and then I'll very briefly discuss how to extend the geometric framework, kind of what its limitations are, And actually, for those of you who came to IGS yesterday, I gave a talk on some work that's going to be released next week that I'm very excited about, where we actually have made some real progress in understanding how to do this. And then I'll conclude, and by the end, you'll be in some superposition of hopefully excited or enjoyed and fried. Okay, so let's get into EFT. Actually, are there any questions so far about the setup? Anything? So what do you do when you build an EFT? Well, it's in principle straightforward. You start by identifying what are the dynamical degrees of freedom, okay? So typically we do that, especially in this context, using fields. Those fields transform under some set of symmetries, say Lorentz symmetry, some internal symmetries. And then we apply some notion of dimensional analysis. In the cases we're going to be discussing here, that's going to be, for example, the ratio of the energy scale of a typical collision at the LHC as compared to the mass of some unknown heavy particles. Okay, and that ratio, as long as that ratio of scales is a small number, then we can do a systematic expansion in that small number. Okay, so that's the role of dimensional analysis. And so when we talk typically in relativistic quantum field theory about mass dimension, we use that to organize our operators in a hierarchy. There we're using this dimensional analysis. There we're assuming that the degrees of freedom we're working with are the only active degrees of freedom in our system, and that all other degrees of freedom are very heavy compared to any experiments we're doing. So fundamentally, maybe you weren't taught it this way. You were just taught to do the dimensional analysis in terms of energy units, right, where a scalar field carries dimension 1, the Lagrangian carries dimension 4, and so on. But that's actually already doing effective field theory. There's an assumption there, which is that there are that you sort of have all of the degrees of freedom that you're working with, and that anything else is heavy compared to the scales of experiments you're going to be describing. Okay, and then of course we just describe this theory as a local Lagrangian, right, in terms of functions of phi and derivatives of phi. And one of the critical things about an effective field theory, one of the things that makes it useful, is that it's local. Okay, so there are examples of non-local EFTs, but typically it's the idea is that you can define some low energy description that's local and analytic, and those two features of the low energy description are kind of critical to the success of the EFT. They tell you if you find something that's, for example, non-analytic, that's typically a sign that you're missing degrees of freedom in the EFT. Okay, so again, this is probably familiar to many of you, but if not, when we work in natural units where C and H bar are set to 1, we put things in brackets, right? So position has units of -1, derivatives have units of 1, the fields have units of 1, and the Lagrangian has the units of 4. And so that allows us, right, to organize operators in this power expansion where this is a relevant operator, this is a marginal operator, and then there's some infinite tower of irrelevant operators suppressed by some heavy scale. But the question that this immediately raises, is what is the physical interpretation of this new heavy scale, right? Because this operator, of course, sets the mass of the light particle. This is some dimensionless quantity, so it's just, something that's hopefully perturbative, so we can use perturbation theory. But this requires some extra information, okay? So the question is how to interpret this scale. So of course, we're doing particle physics, so instead of working with fields, right, we need to go to some kind of particle description. And but the idea of introducing fields is that they naturally account for causality, and they allow us to describe particle production, right? So this is why we move from quantum mechanics to quantum field theory, and in particular, right, an inevitable consequence of making that transition is that particle number is not fixed, which is of course why we do experiments like the LHC. Okay, and we're going to talk about the S matrix, and we'll use Feynman diagrams. Okay, and again, I expect this is probably familiar to most of you. We've seen lots of talks about particle physics. All right, so where do the Feynman rules come from? Well, we start by taking the kinetic term. We set our interactions to 0, and we invert the kinetic term, and that gives us the propagator, right? So the most probably important building block in Feynman diagrams is the propagator, right? Just then when we introduce interactions, now, right, phi cubed gives us a Feynman vertex with 3 lines, and then we stitch phi cubes together using propagators, and we get these 3 momentum structures, right? And so in this case, we've chosen to do some computation of 2 particles phi go to 2 other particles phi in this simple model with only 1 type of particle, right? And this is the combination of these 3 diagrams gives us the matrix element at leading order at tree level. So what does this have to do with EFT? Well, now let's complicate the model a little bit. Let's add a light particle and a heavy particle. Okay, so I'll use color here. The light particle is in purple, the heavy particle is in red. And I'll give, for the sake of an example, I'll give it this coupling. So we have 2 light particles coupled to a heavy particle. And we can do the same kind of scattering process. So 2 light particles go to 2 light particles. And following the same rules, right now we get a propagator with the heavy scale in it. And if this heavy scale, the scale associated with this new particle is much heavier compared to the typical scale of a collision, then we can Taylor expand this propagator. And what we find, right, this is something with momentum dependence in the denominator, but in this limit where P and m, little m, are much, much less than the big M, we can do an expansion and we could get something with only positive powers of momentum, or in position space, positive powers of derivatives, right? And this gives us, again, a local expansion, right, in the sense that we only have derivatives in the numerator. And so, so we have this picture where we zoom out from this process where we know what's going on deeper in the UV, and we get effective interactions at low energies, okay, which we can understand as an approximation in this ratio of physical scales. Okay, so the leading term is just constant, and the subleading term here has this momentum dependence. Okay, so this is the standard use of effective field theory in particle physics, right? We shrink heavy lines to points, and of course this works beyond tree level. It works for higher points, right? So for example, I can have diagrams like this, which give me effective 6-point interactions in the EFT. And again, they're suppressed by 1 over m, and we interpret this. So this gives an interpretation now to the scale m, right? It's the scale associated with whatever the lightest new heavy particles are, which are changing these subtle aspects of our scattering amplitudes. Okay? And there's this slogan here, right, that heavy physics decouples. And this is what we mean. So when we have these corrections to the so-called relevant operators, right, something that's dimension 4, in this case 4 scalar fields in phi to the 4th theory, what we get is something which just corrects this vertex with some constant and then in principle momentum dependence that we could measure. But if we send m to infinity, this just gives us some local shift in the coupling constant. And in fact, this is essentially equivalent to the paradigm of renormalization. Yeah, please.
What happens if I will add tadpole diagram with this heavy particle inside?
Yeah, so that I can also absorb. There I just need to be careful to shift the minimum, right? So when I systematically integrate out this heavy particle, then I just have to account for the fact that that the minimum and the potential in the EFT is shifted with respect to the full theory. But I can include that order by order in the same sense.
My question basically is, how do you know that it will not spoil hierarchy of masses when you start talking about?
Oh, very good. Yeah. So that's definitely so when you have heavy scales, absolutely. in order in this, especially in these toy scalar theories, in order to keep the light particle light, then there has to be some fine tuning that's happening when you cross that heavy threshold.
So there's some assumption though that somehow if you write
Absolutely, absolutely, and indeed, you know, this. So I'm always assuming that this is true, but as you say correctly, I mean, in order, of course, to keep that condition in place, I'm either I'm invoking some additional assumption about the UV that there's some symmetry mechanism to protect the mass, or I'm just tuning. Absolutely. Yeah. So in some sense here, I'm taking very much a bottom-up philosophy, right? We see the light particles in the Standard Model, in particular the Higgs, and we don't know why it's light. And I'm not going to really address solving that problem in the talk. Yeah. Any other questions or comments?
Maybe go briefly back to this issue about locality that you mentioned earlier.
Yes.
So indeed, you said, if I got it right, that if you see some non-analytic or some non-local behavior, it means you miss something. But on the other hand, I guess one of the things we like about these EFTs is that when we look at the non-analytic bits that they predict, such as, you know, they translate to long-range effects, such as corrections to potentials. I mean, have in mind the papers of Donoghue et al. And also more recent developments related to gravitational waves. These are also strong predictions of the EFT. So
very good. So absolutely. So the claim is that what EFT does is it exactly predicts the things you're saying. So the one of the tests when you integrate out heavy particles, one of the checks that you need to do is you want to make sure that at the high scale. So maybe draw this. Yeah. So when we draw pictures like this, right? So at the idea is I have some fundamental theory with heavy particles with some mass associated. I integrate those out, right? And that gives me some EFT at this scale. And the claim is if I have a proper EFT, that all of the contributions to Wilson coefficients that I generate at that scale are going to be analytic in terms of all of the light parameters. So the masses, the momenta, everything else. And then exactly as you say, when I go down to the low scale and I make predictions for experiments, I generate logs of M, logs of kinematics, other non-analytic structure, but that's a prediction, exactly a prediction of the EFT. So the point is of this whole paradigm is that you separate scales. You can isolate the heavy physics as contributions to Wilson coefficients, local contributions to Wilson coefficients, and all sources of non-analytic structure are due to the dynamics of the light modes. And so that's the, in some sense, that's a test of the success of the setup, indeed. Great. Any other, anything else? Okay, so from the point of view of particle physics, ultimately, if we want to systematically search for new physics at the LHC, there's kind of two paradigms that we work with, which are complementary, sometimes overlapping in a good way. Okay, and I would describe them as simplified models. Okay, so by a simplified model here, what I mean is I take the standard model and I add to it some new particle or a handful of new particles. They'll have some interactions with the standard model, and then I can design searches to go look for those new particles. So that's in some sense modifying the standard model directly by just propagating, right, on-shell degrees of freedom. And there's, you know, thousands of papers looking for these kinds of things. Another point of view would be that I instead just want to look at very detailed features of standard model distributions directly. Okay, so for example, I could look at precision Higgs observables, or I could look at tails of distributions. Those are kind of the two classic places where this is helpful. And the idea is, again, I restrict myself to the degrees of freedom of the standard model, but instead of adding new particles, I add these higher dimension operators. Okay, so I'm going to be focused today on thinking about this way of parametrizing beyond the standard model of physics. But as you'll see, actually the lessons I'm going to learn by thinking about the extensions of the standard model as an effective field theory are going to bring me back to motivate a set of simplified models, okay, that I'll discuss at the end. So one of the things I want to communicate today in the context of beyond the standard model physics is the complementarity between these two ways of thinking. At the end of the day, this is all in pursuit of the same goal, right, which is to find some deviation from the standard model, which is going to tell us something about the next new scale in nature. Okay. All right. And so I already said a lot of what's on this slide, but just to say the paradigm in a little bit more detail is we have some fundamental theory. We may or may not specify it. Okay. Then we imagine that fundamental theory leaves its imprint on the standard model by either shifting the already known coefficients or introducing these higher dimension operators. Then the coarse graining in this context is really done by taking this and running the renormalization group down to low scales. That resums a bunch of logarithms. And then at low scales, I work hard to make predictions for experiment. Okay, and that of course involves that consumes people's research careers just trying to do this part, of course. And so this is not an easy task, right? But in principle, if I hand the Lagrangian off to my friends who are experts in QCD, then they can convert that into something that can be compared with experiment. Okay. Let's talk about, and is that the time actually? Where's the time? Time is there. Okay, great. Okay, great. So now let's talk about the connection. Oh, yeah, please. Yeah.
So in this sort of EFT way of thinking, so are there like any assumption that you do to land directly into the, like for starters land into the standard model, and then from there build whatever else it is, or because already you can write like very generic field theories that presumably will have particles that you could observe in principle at the energies that you measured in the standard model. And so from the beginning you have to discard many of those.
Absolutely. So yeah. So I okay. There. I think the right way to think about this is this division is arbitrary in some sense, because I can, of course, I think what you're saying is I can do both at the same time, right? I can, the way I said it is I said in this case, I'm adding new particles and new interactions to the standard model. In this case, I'm assuming it's just the standard model. But of course, I can add new particles, but their effects may only show up as higher dimension operators beyond dimension 4. Absolutely. And I mean, people do think about this. This is maybe an oversimplified picture, but something that I'm going to really stress in this talk is even just if I restrict myself to working with only the standard model degrees of freedom at low energies, there's an additional assumption that people make that they may not realize they're making, which is kind of the thing I want to highlight here. So one of my main messages is that people will often say that working with this effective field theory description is model independent. And I strongly oppose the use of the word independent. We could argue about which word is best. I like agnostic, but it doesn't matter. It's just words. But the point is that there are, the reason people say that the effective field theory approach is model independent is because there's this sense that, indeed, I just parameterize all possible things that could happen. But the way you organize that parameterization has a UV assumption, okay? And so that's exactly the point I want to really stress by the end of the talk, is that this organization, in the way we the standard way we do it, which we call the SMEFT or the SMEFT, has in itself already are built-in assumptions, which I want to talk about ways to break, okay? Absolutely. Okay. So let's talk a little bit about where this connection to geometry comes in, and then I'll come back to particle physics. Okay. So let's go back to 2-to-2 scattering example, just simple scalar fields. And this is just one example, but let's compute the 2-to-2 scattering where I have this kind of dimension 6 interaction. Okay, so it's suppressed by some heavy scale. It has derivatives, which gives me this momentum dependence. Okay, and if you work out the details, this is just algebra. All right, I took massless for simplicity, and I conserve momentum. Then it's a few lines, and you'll find 0. Okay, so I write down an interaction, looks perfectly plausible, right? But then I compute, and I get 0. So somehow something weird is going on here. So is there a better way to understand this? And the answer is indeed yes. It's well known that the fields are not in themselves the physical observables. It's the particles that are the physical observables. And indeed, I actually can choose different parameterizations of the fields, different ways to map from the fields to the particles. And when I do that, I get different looking Lagrangians. And that's known as field redefinitions. So here, just again, to highlight this example, right, I'm showing that if I replace phi by some other field chi with this particular combination, okay, and I just crank through the algebra, I find that this term that I wrote, this interaction, cancels at this order. And so this explains the mysterious 0 that I found in the last slide, because if I pick the right fields, right, the right parameterization, or looking ahead, the right coordinates, then I find that this term vanishes. Okay, so this is of course very well known. This has been known essentially since the prehistory of field theory, and so we can the fact that we can remove interactions with field redefinitions tell us that somehow the Lagrangian is not maybe the best way to parameterize the physics in the sense that it's a redundant description. Okay, so that leads to lots of confusions. First of all, you could ask, how many independent operators are there at some given order in the expansion? That's a very non-obvious question to answer. And in fact, that's been an active area of research in the last, say, 5, maybe going on 10 years, where there are now new techniques that allow us to count the number of independent operators using the so-called Hilbert series, which can account for this kind of ability to remove certain operators that are redundant. There's also been a lot of progress in understanding the general parameterization and the implications. So for example, in this paper, just again to highlight my own work, we recently revisited the proof of this fact and actually found some interesting effects at loop level. And in particular, we rediscovered, in a sense, something that was known in the 70s, which is that field redefinitions, even non-local field redefinitions, are allowed, but there's a little bit of extra work you have to do to maintain the self-consistency of the theory. And so I think we reviewed and kind of repackaged the proof of field redefinition invariance in a perturbation theory in a way that I think is, that I hope is clear and had some nice implications. Okay, so what does this have to do with geometry? Well, let me remind you, when we talk about geometry, we're going to talk about, we're going to use a metric, right? That metric's going to be an input to compute things like a Riemann curvature tensor and so on. That metric has properties. It's a 2-index tensor. It's symmetric and it's invertible. And if I can identify an object with these properties, then that gives me a metric in some space. Okay? So what does that tell me? Well, that allows me to discuss things like curvature, right? But it also gives me a notion of, sorry, when I'm talking about tensor structure, I'm really talking about a notion of changing coordinates. So for example, right, I can do a rotation and I can change my coordinates from x to x prime. And this rotation matrix transforms as a 2 tensor, okay? And so in particular, right, under a general coordinate transformation, I have this transformation rule. So this is all just standard stuff from, GR, differential geometry. And then I can check, because I have this transformation rule, right, under rotations, that the metric transforms as a 2 tensor, okay? So again, I imagine that this is all stuff that's familiar, okay? So of course, in Minkowski space, we write the metric, say, as mostly minus in this way, right? It's diagonal with time and space, okay? So now, what does that have to do with effective field theory? Well, I can write a generic effective field theory in the following way. I can parameterize the coefficient of the 2 derivative term with some matrix. This is something that depends on the fields. So now this I and this j index are indices in the field space. So I now imagine I have many fields. And mu and nu are Lorentz indices. So these are derivatives in space-time, okay? And for example, right, I can write this metric as 1. I need the 1 because I need the kinetic term for all the fields, and then plus some interactions, and this, of course, is in principle goes on and on. So now I can perform one of these field redefinitions, right? I can send phi to phi prime, which is just some polynomial in the fields, and I can see that there's an analogy with changing coordinates, because this term that appeared in the Lagrangian changes. I just added primes here, but that's equal to something that changes with this tensor-like transformation for G, okay? So I can identify that this object that appeared in front of the kinetic term in this IPHT Lagrangian, this way of writing the effective field theory, transforms as a 2 tensor. Furthermore, it's symmetric because it appears in front of this symmetric term, so it's symmetric in I and J. And because I enforce that I have kinetic terms for all of the fields in the theory, that tells me it's invertible. And so indeed, I can interpret this quantity that appeared in the Lagrangian as a metric, okay? And actually, to my knowledge, this was first written down by Volkov in this really beautiful paper in 1973, okay? So now that I have a metric, I can interpret the IPHT as living in on some manifold in some geometric space, and I just take my favorite GR textbook and I turn the crank and I outpop all of the things that are familiar from GR. So I can get curvature tensors, Ricci scalars, covariant derivatives, and so on. Okay. So again, I haven't done anything except package the Lagrangian in a suggestive form and then identify that that there's some object that has the right properties to be a metric. All right, so now, what does that metric buy me? Well, I can, let me again take this way of writing the IPHT Lagrangian, turn, again, my favorite crank, and outpop scattering amplitudes. And it turns out that the scattering amplitudes take the following form. So they look like something which is the Riemann curvature tensor. These are the external indices associated with these lines in the Feynman diagram, okay? For those of you who heard my talk yesterday, right, here I'm being a little sloppy. So this is actually for experts, this is the amputated correlation function, not the S matrix element, but that's just a little detail. But the idea is, right, that the indices here correspond to the indices in the Feynman diagram, and there's some Riemann curvature tensor appearing, basically that reflects the fact that S matrix elements need to be field redefinition invariant. So this thing where I've exposed the external indices has some covariant-like structure, okay? So it's, on the one hand, when you do this calculation, it's non-trivial, okay? So it's actually quite remarkable. It's a couple of pages of algebra, and you have to use Bianchi identities and various things from GR. Okay, so and Volkov knew this, by the way. These formulas appear, I think, in the paper even in the 70s. But but it's kind of a remarkable, in hindsight, you might say, oh, well, we knew this thing was invariant, so of course it had to be built out of the natural invariance. But nonetheless, I mean, it's non-trivial. And when you go to more complicated diagrams at higher points, what you find are these same objects, but then with covariant derivatives in field space acting on them. And I should emphasize, this is a tree-level formula, of course. Yeah.
My question, so you're talking about tree level.
Yes.
But then how do you know that this is definition which you presented previously in the interacting theory is a free of the normal?
Yeah, so so you're worried about loops generally. I mean,
In general, I would
yeah.
say that as soon as you turn on interaction, you're expecting the symmetry which you presented to be broken.
Yeah, so absolutely. So so there are so you might think that this is all a tree level accident.
Unless you have the symmetry and ensuring the symmetry is exact.
Yeah, well, and so indeed here, of course, I'm going to apply this to the Standard model where the symmetries are going to be the symmetries of the Standard model. Okay, so then I will be in a case where there's symmetry. But I'm naturally a skeptic, so I mean I think these results are they're nice, but yes, it's very natural to expect that all of this breaks down once you start including loops. What's remarkable, actually, is not me, but other groups who've been working in this subfield, mostly driven by the group out of UC San Diego with Anish Manohar and collaborators, have computed RGEs for effectively applying this to the standard model EFT. So they can write the standard model EFT RGEs completely is in the same language using these geometric objects. So it appears at least at one loop to be preserved and that there's a useful description there. There's a group, actually collaborators of mine, I was involved, who have done this EFT matching step at one loop, and they can show how to do that, preserving all of the geometric quantities, so everything can be expressed in terms of Riemann curvature. There's also, here I'm talking about scalars, but people have been working on including fermions, so there's a number of groups who've done that. So far, all of the attempts to see this as a more general statement about the behavior of scattering amplitudes and the connection between geometry and amplitudes is holding up, but you know, it's very much an active field to understand what are the limitations of this connection.
Just probably another question that so this theory have not been studied for ages in two dimensions. So the two-dimensional sigma model, people know beaten to death this model in two dimensions, and we know basically everything about two dimensions.
Yeah.
And basically my question was driven by what we know from two dimensions.
Sure.
So you're saying that in 4 dimensions, all those problems people found in 2 dimensions just shift towards higher loops?
So I'm saying that if I interpret the interpretation that I'll give to this, which is I'll work in sort of a toy standard model where I have, you know, I'm going to have SO4 symmetry instead of SU2 cross U1 because I have custodial symmetry just to simplify things. But in cases where I'm going to interpret this EFT as the scalar sector of the standard model, for that particular case where people have done calculations at least up to one loop, and they don't seem to find any flaws in the map, in the geometric map. But I think nobody is. There's a lot of open questions. I mean, I have personally things that I haven't had a chance to explore yet, but I think that there will be. Well, maybe I can make some comments at the end once because there are another thing. Maybe another part of what I haven't emphasized yet, which will address your question, is here. I should have said it. So here, I'm restricting myself to field redefinitions without derivatives. And one of the frontiers, one of the things that I've been working on in particular, is whether or not any of this exists when you include field redefinitions with derivatives, which is actually the thing that's useful for us in the particle physics context. And so we have some proposal for how to extend the framework, but it's not it's not just an obvious extension. It really requires some repackaging. So yeah, so there's lots of in some sense, I should have said that, I call it generic here because it's a colloquium, but, I really think of this as a toy model of EFT, right? So this is a very restricted class, but we are seeing these nice features and then, well, I'm going to tell a story here using this that we learned something that's relevant for phenomenology. Okay, so good. So I just want to mention quickly one trick when you're doing these amplitude calculations, if you get interested in this subject. You'll see very quickly when you dig into the papers that normal coordinates, right, where you pick the coordinate system, say this is the physical vacuum in the field manifold. If you pick the coordinate system that corresponds to normal coordinates, you do a field redefinition. What that does in practice is that causes the 3-point function to be 0. So you can basically you can use the GR technology to find this coordinate system, which has this nice interpretation in GR, but the implications in the Feynman diagrams in the particle physics context is that it sets the 3-point function to 0. It pushes it into the higher point vertices, and that makes life a lot easier. And in fact, if you want to derive these formulas, the 2-to-2 scattering formulas are almost trivial to derive if you work in the special coordinate basis. And so going to higher point, again, is harder work, but everything is much easier in normal coordinates. And in this paper, we use this normal coordinates to actually compute the leading in energy scattering of 2 Goldstone bosons with any number of Higgs bosons. And we were able to do that in this geometric language, again, because normal coordinates really make the calculations tractable. Okay. All right. So that's the connections between the geometric picture and effective field theory. So now let me talk a little bit about applications in the last 10 minutes. Any other comments or questions before I move on? Okay. So I've already said this a little bit, but of course the application to the standard model and to the standard model as an EFT is to think about the Higgs sector. So here we have the standard wine bottle picture, right, where we have the Higgs at the origin of field space, and we have the Higgs mechanism where we give the Higgs a non-zero vacuum expectation value, and that gives us electroweak symmetry breaking, and so this is where we live, right, is in the physical vacuum that's at the bottom of the wine bottle. And of course, the Higgs mechanism gives us this phenomenon of eating degrees of freedom and so on. What I want to emphasize here is in the talk, I'm going to just be talking about the scalar sector. So I'm going to talk about the Higgs, and I'm going to talk about the Goldstone bosons, right, the longitudinal modes, okay? So what does this have to do with effective field theory? Well, it turns out that for the standard model, there's 2 ways you could imagine parametrizing the EFT describing beyond the standard model physics. The first is the kind of obvious thing that you would do if you were starting with the standard model as we typically define it, SU3 cross SU2 cross U1 with a Higgs doublet, and you would just add higher dimension operators to that. And that's what most people do. That's kind of the standard thing, and that's known as the SMEFT, right? The standard model EFT. You can think about that as expanding the theory at the top of the hill here, right? And from the geometric point of view, you can think of that as Cartesian coordinates. And that's in contrast with what has this kind of unfortunate name, but now this is how we all just call it, is the Higgs EFT, or HEFT, okay? Which is the EFT which is defined directly in the broken phase. So for the experts, right, here we do a CCWZ type construction, right? We treat the Goldstone bosons as a nonlinear sigma model, and the Higgs boson as just some singlet degree of freedom. And you can think about this as expanding the theory in a polar coordinate system, okay? And so I'll use the notation H for the physical Higgs, pi for the Goldstone bosons, and I'll compare that with capital H, which is the doublet in the unbroken phase that lives up here. Okay. So that might seem like an innocuous thing, but when you're building the theory from the bottom up, you write all possible operators, and it turns out that the SMEFT has less independent parameters than the heft. The heft description is more flexible. It accommodates a wider range of phenomena. And in particular, I'll highlight the kinds of theories that live in this region that is heft but not SMEFT. Okay? So in some sense, the central question from a particle physics point of view here is, I'm a theorist. I go and I try to motivate my experimental colleagues that they should look for tails of distributions for very sensitive observables, which is going to tell them something about the next scale of new physics, as in the sense that I've been describing in this talk, right, as a contribution to an effective field theory. And I tell them this is an extremely general approach, and so you should organize your thinking this way. You should pick these observables first because they're motivated. They show up at leading order in the EFT expansion, and so on. But that leaves an open question, which is, are you covering all possible scenarios of heavy new physics? And the claim that I'm going to make is that no, there are a set of models that live in this region, even weakly coupled models that we can describe in perturbation theory, that live in this region where the SMEFT description would miss them. Okay. Why was this an open question until we wrote this paper a few years ago? Well, the answer comes back to this nasty thing about field redefinitions, which is that you can obscure the physical content of the EFT by doing a field redefinition. So, even knowing, again, the number of independent couplings that lead to physical observables is a hard question. And so you might think, oh, yeah, it's trivial. I hand you a Lagrangian, and you can just check. Does that Lagrangian, can I basically take the Lagrangian defined at the physical vacuum, and can I just move all the fields to the origin and get something that's local and analytic and has all the right properties? And the answer is no, because you can do a field redefinition, which completely obscures that map. Okay? And if you're curious, in our paper, we show some completely ridiculous examples. In fact, you can just take the free theory defined at this point. You can do a simple polynomial field redefinition, and then when you try to extrapolate that back to the origin, you find something that's horribly non-local and non-analytic. Okay? Yeah.
Question. I'm not an expert in this, but because you do your is doing it in the broken phase and the SMEFT is doing it in the unbroken phase. So is it the reason why the heft has a larger coverage than the SMEFT? It seems like because you are in the broken phase and you choose your different degrees of freedom. It looks to me like you don't know where these degrees of freedom actually rooting from. Meanwhile, in the SMEFT, you already take, it's a doublet and the Goldstone bosons come from the specific breaking. So it looks like the reason why it shrinks is because you include more data in your parameterization from the beginning. So should not, now that we are living in the standard model, so say that the additional when we want to search for new physics, it has the coverage. The SMEFT is sufficient because we know it should live in the SMEFT region, or am I wrong in this?
Okay, so everything you said up to the last sentence was completely on point. Okay. But I'm going to give examples of simple theories that live in this region. Okay, so it was surprising to us that this wasn't all well-known stuff. But if you bear with me a few slides, I'm gonna tell you. I'm gonna try to convince you that there are targets to look for, basically to rule out the edge cases, so that we really do know that the SMEFT description is capturing all possible that phenomenologically the SMEF description is capturing all things that could exist and that we could observe. But yeah, it's kind of surprising. You would think that there would be that given what we know about the standard model, that we would know that we just live in the SMEF, but that's not true. There's something I thought you might say, okay, which is that I'm cheating a little bit here when I draw this picture, okay? I'm being imprecise because the dimensional analysis in SMEF and the dimensional analysis in HEFT is actually quite a bit different. And always when you talk about an EFT, you really need to specify, I'm working with an EFT up to some order in the expansion. And so there's something I'm happy to talk about offline, but I'll just plant the seed of this, which is that I'm being imprecise because I'm not telling you SMEF up to some dimension. I'm just calling it SMEF, and HEFT up to some different dimension because the dimensional analysis is different. It's organized differently. Okay, and so there's a question there. There's something additional, but the cartoon is correct. And they're only, in some sense, the map from SMEF to HEFT, even in the region where they overlap, is only exact when I go to all orders in the expansion. Okay. So there's some additional little additional thing on top of this to worry about. I think I wrote this. Let's see if it still works. Okay. All right. So I'm out of time. So I don't have time to give you the argument. Okay. We have a long proof of this in the appendix of this paper from now 2020. So a few years ago. But the slogan, what I wanted to call the paper this, but we decided to go with something a little more mundane because it's not a very precise analogy, but I like it as a slogan, which is that HEFT is a black hole. Okay. So there are basically two. We used this given these statements. Okay. Given what I told you about field redefinitions obscuring the difference between these EFTs, then the motivation was, well, maybe we could use this geometric framework, which is independent of the parameterization, to come up with a criterion to tell us whether or not we're in a SMEF theory or a HEFT that can't be SMEF theory. And in fact, we were able to prove such a criterion. And what it told us is that once we had it, basically the criterion says that in the manifold for the scalar fields, there has to exist a point where electroweak symmetry is restored, and there's a precise notion in the EFT language of how to find such a point. In fact, the Manohar, Jenkins, and Alonso already had established that for us in their seminal work on this subject. Then there's an additional requirement, which is that once we go to that point, all of the curvature invariants we compute in the EFT are finite. And it turns out that those two kind of natural conditions allow us to define the region, which is where I can take a HEFT and I can rewrite it as a SMEF Lagrangian. Okay? So that's the claim. And once you have that claim, then you can start to explore, well, what kind of theories violate one of those conditions? And there's basically, in perturbation theory, there's two classes of theories that violate that condition. One is that there exists what I'll call a horizon. Okay? Again, this is a loose analogy, but just so we have a fun slogan. And the horizon is when I can't get to a point on the manifold where electroweak symmetry is restored. Okay? And that manifests in a BSM context as having a theory with a new source of electroweak symmetry breaking, right? That says that the W and the Z, from the point of view of just the low energy degrees of freedom of the standard model, anywhere I move on the manifold for the Higgs, any VEV I give to the Higgs, there's no point where the W and the Z have zero mass, because there's some other source of electroweak symmetry breaking that I've integrated out that I'm not including, right? So I can't find the point in the manifold where the W and Z are massless. So we call that a horizon, and that's theories with extra sources of electroweak symmetry breaking. From a phenomenological point of view, there is some parameter space for such things, but it's pretty tightly constrained. And it's sort of well known and enumerated how to basically add. For example, you can have a 2 Higgs doublet model that's an extremely well-studied subject, or you can have, say, you can add a triplet Higgs to the standard model, but that leads to large corrections to precision electroweak observables. And so we know already from LEP that having a VEV or a vacuum expectation value for a triplet Higgs is highly constrained. It has to be small. Okay. The other case, which is really the new feature for us, is when these curvature invariants blow up, you can identify the source of that as being coming from having integrated out a field that gets all of its mass from the Higgs. So the standard model has particles that get all of their mass from the Higgs, right? All of the fermions are like that. So basically, the point is that if there's some BSM physics that also gets all or even most of its mass from the Higgs, where we can make most precise using these geometric criteria, it's roughly half, depends on the details of the model, then that leads to some singularity on the manifold. And so, again, in analogy with black holes, we'll call that a naked singularity. And so that's coming from some BSM state whose mass is coming from the Higgs. And the intuition is just that when I try to go back to the origin where the Higgs VEV turns off, now I have a massless degree of freedom. And so I've effectively integrated out something that's massless, which violates the central idea of EFT, right? Which is that I'm integrating out heavy things. Okay, so good. So I already said this, and in fact, this motivated us to revisit the EFT that you get in the 2 Higgs doublet model. If that's something you're interested in, we have this paper where I think we provide a really nice geometry-inspired matching for the 2 Higgs doublet model. Anyway, I'm 5 minutes over. So yeah, so let me just flash. The last thing is just that basically once we realized that there was this class of models that live in this wedge that is Heft not Smeft, then you can basically just sit down and try to classify all of them and ask about their phenomenology. And it turns out most of them are dead, right? They're constrained by some combination of LEP and LHC, but there are a few examples where there's still some open parameter space. Here, the details don't matter, but I'm just plotting the fraction of the particle mass that comes from the Higgs versus its mass. And there's various constraints, theoretical constraints like perturbative unitarity. Here, this is constraints on the Higgs couplings. There's Higgs decays and direct searches, okay? But the point is that these, we called them Lorions because we didn't know what else to call them. So my collaborator, Nathaniel Craig, had to fit against Wake on his shelf. And so he took inspiration from Gelman and found this funny word. But anyway, the point is that there are current and future prospects for looking for these things. Okay, so they provide us with a nice target for current ongoing searches, but also future colliders. Okay, I'm out of time. Let me just say, I already mentioned, right, this geometric framework is actually quite restrictive. And we've been working hard in the last few years to just understand how to apply it to general EFTs beyond this toy model. And of course, now that so next week, we're going to post a paper where I think we finally have figured out, at least at tree level, how to extend the framework to accommodate field redefinitions with derivatives. We have some previous failed attempts, and we've learned things over the years about what this geometry should look like. And now I think we finally know how to write something down. And so keep an eye out for that if you're curious. But there's still a lot of work to do. And of course, then applying that to the phenomenological cases is an obvious next step. Okay. Yeah, hopefully I said something that was of interest to everybody. I talked about this general idea of EFTs. I discussed that it applies in many contexts, but in particular here, I was discussing the application to beyond the standard model physics. And then using this connection between effective field theory and geometry in order to characterize scenarios for new physics, which basically have this kind of non-decoupling behavior, which violates the central approximation of the SMEF. So I said earlier, right, when people say that the SMEF is model independent, this is clearly showing that there are examples of theories of UV choices which don't fit in this MEF framework. And so, in some sense, the question is, can we systematically rule out heft, right? So we don't have to be talking about this anymore, and we can parameterize going forward all of our new physics effects just using this description, which is easier to interpret. It's still a hard problem, but it's easier to interpret. Okay, and of course, in the future, right, we want to maybe discover something, but also extend this idea of the geometry. And there's lots of other more theoretical work on geometry. You can talk to Julio Martinez at IGS. He's written some very cool papers on aspects of this too. And I'll just leave you with my slogan. Sorry for going over. Thanks for your attention.
Last team, and I guess we have a couple of minutes for the questions, comments.
It was a nice talk. I was wondering if this geometrical picture as something nice to say. For example, if you look at the Wilson coefficients in EFT, if I focus on the ones which are the same order in power counting, does it provide some nice picture in this geometrical setup? Or maybe more concretely, if I impose some symmetries, some extra symmetries, how does it reflect in the geometries, like symmetry of the geometry?
Yeah, so to your first question, the interplay with the power counting is kind of at the edge of research questions, the current research questions. So there are most of the work that's been done in the subject has been really in this toy context of the two derivative theory plus a potential. And even there, there's surprisingly rich structure, and there's a lot of work on understanding basically how to, like I mentioned earlier, how to compute renormalization group evolution equations in that context, or matching coefficients, or various other things, compute higher point amplitudes. There's also a forthcoming paper by some friends of mine. We're going to coordinate with them next week on interpreting this in terms of jet bundles, right, and extending the geometry so they can incorporate the potential in what they call the zero jet bundle, and they're trying to use that as a stepstone to building to the bigger geometry and so on. So I think as far as like adding higher dimension operators, understanding how they feed into all of the structure, there's some modest progress in that direction, but it's not a systematically understood subject yet. And then as far as symmetries go, yeah, I mean, absolutely, those field indices, right, are going to also transform whatever symmetries you impose, right? Those are going to be symmetries that are encoded in the properties of those field indices. So if you have some subset of indices which are closed under some symmetry transformation, that subset is going to be reflected somehow in the geometry, right? Because there's going to be some subspace. Of course, but yeah, I mean, one of the nice things about this is that it's very flexible, and so it can just sort of accommodate anything, right? And so yeah, so as far as like framing tests of so if you wanted to good. I don't know of anybody who has tried to formulate identifying symmetries by studying maybe properties of the geometric objects directly. That might be trivial, or that might be interesting. I'm not sure, but yeah, I haven't thought about that specifically.
Hey, I also have two questions. The first one, I think the most important one, can you do something like gauge invariance? So can you see also the gauge invariance in some way, somehow, just like the same way as some kind of filter definition like thing? That's the first one. And the second one is if you could comment a little bit on if there is progress. You mentioned it at one point, but I don't know, but I would like to know what is the status for higher spins if you are apart from scalars.
Good. So to your first question, actually the original proofs of field redefinition invariance and all of the worries about this stuff goes back to gauge invariance, because a gauge transformation indeed is a field redefinition. As far as the interplay, and there's like a long history of both in gauge theories and gravity, there's this Vilkovisky-DeWitt approach to the path integral, for example, which is somehow trying to covariantize, I don't understand what they did, but it's somehow trying to covariantize the source terms in the path integral to accommodate for field redefinition. They're really to accommodate for gauge transformations. So these things are deeply connected, but most of the sort of resurgence of this, which was really spurred by this application to the standard model EFT by Alonzo Jenkins and Manohar in 2016 in a couple of papers, has been mostly focused on the scalar sector. And there's been kind of surprising richness just there, but absolutely gauge bosons are in all of our minds. And somehow we would like to see how to accommodate gauge bosons in this framework in a natural way, because it should be possible, but it's going to require some extra ideas, right? So you need to understand gauge fixing, and maybe there's a way to geometrize that, right? So on. For fermions, that's a place where there is more progress. So there are a number of groups that have proposals that basically allow you to extend, the indices on the metric are field space indices. So there's a way to kind of take that into superspace and extend those to fermionic indices. And in fact, there was a paper just this past week from the group out of UC Santa Barbara, Nathaniel Craig and his students, where they have, in this context of the two derivative theory, they've made further progress in including fermions. They have some nice new calculations of scattering amplitudes for Goldstone bosons to fermion scattering, basically. And they can show that again, like the one example I showed here, they can write some really nice formulas which are purely geometric for that kind of scattering. But that's a kind of a frontier. I mean, that paper came out last week. So people are thinking about these things, but it's not a solved problem. I would say it's not a closed problem. It's still very much ongoing. Yeah. The nice thing in that paper, though, is I think it's a very nice paper, because they were really trying to push Nathaniel Craig's one of my collaborators on this stuff. So they were here. We assumed custodial symmetry. We had no fermions. So they were trying to take some of the statements that we made and bring them closer to the real standard model. So they, in particular, in that paper, they introduced custodial violation. They have sort of a top and a bottom fork, or toy model for that, right? And so they can really add more and more realistic features to all of this and show how to accommodate it in a generalization of the framework. So I'm not surprised to know that those things can be done, but now it's nice to have it actually concretely worked out.
Do you need or do you want a field band on field space?
Very good question. So the Veilbein plays a critical role in the whole story, actually, which is that it effectively acts as the wave function renormalization factor. So you can because the metric is the two derivative term, and so it's closely related to the propagator, diagonalizing the propagator is accomplished using Veilbeins. And so then the geometric formula for the scattering amplitude is actually contraction of the Veilbeins with those formulas. And so yeah, they actually come up very naturally in this context.
Okay, any other further comment or question? No. We can thank him again for the
Thanks, everyone.
So, in housekeeping details, I guess the people that